Welcome back. Last episode, our spring was always left alone. Pull it, release it, and it winds down to rest. Today, we refuse to leave it alone. We push it rhythmically from the outside, adding a driving force to the equation mx double prime plus cx prime plus kx equals f naught cosine omega t. Here, f naught is how hard we push, and omega is how fast we push. That small change unleashes some of the most dramatic behavior in all of applied mathematics. The response splits into a transient that fades and a steady state that locks onto our rhythm. We will meet beats, the slow throbbing when you drive near the natural frequency. We will meet pure resonance, where the amplitude grows without any bound. And we will see practical resonance, the towering amplitude peak in real damped systems. This is the math that shatters wine glasses, tunes radios, and, infamously, brought down a bridge. Start with the structure. Our equation is now non-homogeneous. There is a forcing term on the right-hand side. From earlier episodes, we know the general solution is the homogeneous solution plus any particular solution. Both pieces have a beautiful physical meaning here. The homogeneous part, x sub h, solves the free equation, the unforced spring from last episode. If there is any damping at all, it decays to zero. So we call it the transient. It depends on how the system started, but it fades away and is soon forgotten. The particular part, x sub p, is driven by the external force and oscillates at the driving frequency omega, persisting for as long as we keep pushing. We call it the steady state. The lesson is that after you switch the forcing on and wait a moment, the startup wiggles die out and the system settles into a clean oscillation at exactly the frequency you are driving it. The steady state is what survives. Let's actually find the steady state. Since the forcing is a cosine, we guess a particular solution that is a cosine plus a sine at the same frequency by the method of undetermined coefficients. Equivalently, we write it as a single cosine with amplitude r and a phase lag delta. Substituting into the equation and matching coefficients gives the steady state amplitude r of omega, f naught divided by the square root of the quantity k minus m omega squared plus c squared omega squared. Stare at that formula because it is the heart of the whole episode. The amplitude is large exactly when the denominator is small. In the undamped case, with c equal to 0, the denominator simplifies to the absolute value of k minus m omega squared, and that becomes 0 when omega equals omega naught, the natural frequency. At that point, the amplitude formula blows up to infinity. That explosion is resonance, and the rest of the episode is about exactly what happens as you approach it. The phase lag delta tells you the response runs behind the push. Now the first dramatic case, an undamped spring driven near, but not exactly at, its natural frequency, starting from rest. The solution turns out to be a difference of two cosines, one at the driving frequency omega, one at the natural frequency omega naught, scaled by a factor that grows as the two frequencies get close. Two cosines of nearly equal frequency interfere, and there is a trigonometric identity that reveals what that interference looks like. The product to sum formula rewrites the difference as a product of two sines, a fast one oscillating at the average of the two frequencies, multiplied by a slow one oscillating at half their difference. So you hear a rapid tone whose loudness swells and fades slowly. That is the phenomenon of beats, the throbbing wah-wah you hear when two guitar strings are almost but not quite in tune, or when two aircraft engines run at nearly the same speed. The closer the two frequencies, the slower and more dramatic the throb. Now drive the undamped spring exactly at its natural frequency, with omega equal to omega naught. Something special happens to the mathematics. The forcing term is now a solution of the homogeneous equation itself. It is driving the system in perfect step with its own natural rhythm. The method of undetermined coefficients tells us that when the forcing duplicates a homogeneous solution, we must multiply our guess by an extra factor of t. The result is a particular solution proportional to t times sine of omega naught t. Look at what that means. The amplitude is no longer constant. It is f naught over 2 omega naught, all multiplied by t. It grows linearly with time, climbing higher and higher without any bound. This is pure resonance. Physically, every push delivers energy in perfect synchrony with the motion, and with no damping there is nothing to drain it away, so the energy and the amplitude just accumulate forever. It is an idealization. Real springs have damping, but the warning it gives is absolutely real. Here is the single most important picture in the episode, the steady-state amplitude plotted against the driving frequency, for several different amounts of damping. The horizontal axis is how fast you push. The vertical axis is how big the resulting steady oscillation is. The dashed vertical line marks the natural frequency omega naught. With light damping, the curve has a tall, sharp gold peak right around the natural frequency. Drive there and you get a huge response for a modest push. That peak is practical resonance. As you add more damping, the peak gets lower and broader until heavy damping flattens it into a gentle hump. And as damping shrinks toward 0, the peak shoots upward toward infinity, recovering the pure resonance we just saw. One subtle detail worth noticing: with damping present, the peak sits a little below the natural frequency, not exactly on it. The lighter the damping, the closer the peak creeps to omega naught, and the more dangerous it becomes. Real systems always have some damping, so the amplitude never literally reaches infinity. Instead, it rises to a finite but possibly enormous peak. Calculus tells us exactly where. Maximize the amplitude formula over the driving frequency, and the peak occurs at the practical resonance frequency omega max, which equals the square root of omega naught squared minus c squared over 2m squared. Notice that this is slightly less than the natural frequency. Damping pushes the peak down a little. When the damping is light, the peak is tall and narrow and sits very close to omega naught, and its height is roughly f naught divided by c times omega naught. Because c is in the denominator, small damping means a gigantic response. When the damping is heavy enough, specifically when c squared exceeds 2mk, the peak disappears entirely and the amplitude just decreases with frequency. This single peak is double-edged. It is how a radio tunes in to one station and ignores all the others, and it is how a singer holding exactly the right pitch can shatter a wine glass. Let's compute a beat. Take the undamped equation x double prime plus 64x equals 16 cosine 7t, starting from rest. The natural frequency is the square root of 64, which is 8, and we are driving at 7, close but not equal. The steady-state guess is a cosine at frequency 7, and matching coefficients give 16 over the quantity 64 minus 49, that is 16 over 15, times cosine 7. T fitting the homogeneous part so the system starts from rest gives the full solution, 16 over 15, times the difference cosine 7t minus cosine 8tt. Apply the product to some identity, and that becomes 32 over 15 times sine of t over 2 times sine of 15 over 2. So we have a fast oscillation at 15 halves interacting with a slow envelope at 1/2. The slow envelope swells and fades with a period of 2 pi divided by 1/2, which is 4 pi seconds between throbs. That slow throbbing is the beat. Now nudge the driving frequency from 7 up to 8, so we drive exactly at the natural frequency, x double prime plus 64x equals 16 cosine 8t, again from rest. This is the resonant case. The forcing, cosine 8t, is now itself a solution of the homogeneous equation, so undetermined coefficients demands an extra factor of t in our guess. Plugging in, the resonance formula gives f naught over 2m omega naught times t sine 8t. With f naught equal to 16, m equal to 1, and omega naught equal to 8, the coefficient is 16 over 16, which is 1. So the solution is simply x of t equals t sine 8t. Compare this to the previous example. There, the amplitude stayed bounded at 16/15. Here, the amplitude is the envelope absolute value of t, which grows without limit. Every oscillation is larger than the one before it, and the motion climbs forever. That single factor of t, forced on us by the repeated root, is the entire mathematical signature of resonance. One last example, this time with damping. Take x double prime plus 2x prime plus 26x equals 10 cosine omega t. So the mass is 1, the damping is 2, the stiffness is 26, and the natural frequency is the square root of 26, about 5.1. We want the driving frequency that produces the biggest steady-state amplitude. Use the practical resonance formula, omega max equals the square root of omega naught squared minus c squared over 2m squared, which is the square root of 26 minus 2, the square root of 24, about 4.9. Notice it is a touch below the natural frequency of 5.1, exactly as predicted. Now find the amplitude there. Plug omega max into the amplitude formula. The denominator is the square root of k minus m omega squared, plus c squared omega squared, which works out to the square root of 4 plus 96, the square root of 100, which is 10. So the peak amplitude is 10 over 10, equal to 1. Damping kept the response finite, and calculus told us precisely where and how big the peak is. A little history and one famous caution. The intuition for resonance is old. Galileo noticed that small, well-timed pushes can build a pendulum into large swings, and anyone who has pumped a playground swing knows it in their body. In the 19th century, Helmholtz and Lord Rayleigh built the rigorous theory of resonance in sound and vibration. Resonance is enormously useful. It is how you tune a radio to one station, how an MRI machine works, and how every musical instrument selects its tone. But it is also dangerous. Soldiers are told to break step when crossing a bridge, so their marching does not drive it at its natural frequency, and rotating machinery is carefully designed to avoid its resonant speeds. The most famous warning is the Tacoma Narrows Bridge, which tore itself apart in a wind in 1940. It is often described as simple resonance, and as a vivid caution that is fair, though the truer cause was a related self-driven instability called aeroelastic flutter, not a pure external drive at the natural frequency. Either way, the lesson holds: respect the resonant frequency. Let's recap. We drove the spring with an external force, giving mx double prime plus cx prime plus kx equals f naught cosine omega t. The solution is a transient plus a steady state. The transient solves the free equation and fades to zero when there is damping. The steady state oscillates at the driving frequency forever, with amplitude f naught over the square root of the quantity k minus m omega squared plus c squared omega squared. 3 dramatic cases. Drive an undamped system near the natural frequency and 2 close cosines interfere to make beats, a slow throbbing envelope. Drive an undamped system exactly at the natural frequency and you get pure resonance, a term proportional to t sine omega naught t that grows without bound. Add damping and the response is capped, peaking at the practical resonance frequency just below omega naught. Resonance tunes radios and shatters glasses, and the Tacoma Narrows Bridge is its famous warning. Next episode, the Laplace transform turns these differential equations, forcing and all, into pure algebra. Today we push the spring from outside. The forced equation is mx double prime plus cx prime plus kx equals f naught cosine omega t, where f naught is the amplitude of the driving force and omega is the driving frequency. Its general solution splits into 2 pieces. The transient is the solution to the free equation we already solved, and damping makes it fade to nothing. The steady state is a particular solution that oscillates at the driving frequency forever, with an amplitude that depends sharply on how close omega is to the natural frequency omega naught. With no damping and a driving frequency near but not equal to the natural frequency, 2 close cosines interfere to make beats, a slow throbbing of the amplitude. Drive an undamped system exactly at its natural frequency and you get pure resonance, a particular solution that grows like t times cosine omega naught t, climbing without bound. Add damping and that growth is capped, but the amplitude can still peak hugely at the practical resonance frequency, which sits just below omega naught. This is why a singer can shatter a glass and why soldiers break step crossing a bridge. The Tacoma Narrows Bridge is the famous warning. Next time, the Laplace transform turns all of this into algebra. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.